Yes, I think you can start sharing your screen.
So your Zoom reminds about recordings. That's very good. My Zoom doesn't.
The University of Amsterdam is worried about privacy. That's why they have this setting.
But due to that, I often forget to switch it on.
So this is also, it's useful to have more than one host, right? It's this way, at least one person would usually remember. Okay, so we are ready to start the second talk of this session. So this is paper by Harris, Aziz, and Florian Randall. Harris is giving the talk. He will be talking about the vigilant eating rule, and a general approach to probabilistic design with constraints. See that Florian was in the audience, so hopefully if there are questions in the chat, Florian. Okay, welcome, Harris. So the floor is yours.
Thanks, Edith. Can you all hear me? All good? Okay, so as Edith said, this is based on joint work with Florian, and since he's in the audience, hopefully he will field all the tough questions. In this particular presentation, I will be discussing a rule called the Vigilant Eating Rule. It's a rule that we propose in this paper. And this rule applies to many economic design problems. But as a starting point, it's probably best to think of a very basic object allocation setting in which agents have ordinal preferences over objects, and they want to get one object each. So this particular talk, it's in the wider umbrella of resource allocation and matching. And as you all know, one of the major success stories in algorithmic economics is the application of matching algorithms in various application domains. So one pattern that arises here is that new applications, they give rise to new constraints, be they physical constraints, for example, maximum number of students per course. They may be affirmative action diversity constraints, or they could be individual rationality requirements. In this particular paper, we will even take stability requirements as feasibility constraints. Another bit of background for this work is that we are interested in probabilistic or random allocations, which specify the probability of an agent getting each item. Why should we care about randomization? Well, randomization is very important to achieve fairness properties such as anonymity and ex-ante equal treatment of equals. Mathematically speaking, specifying a probability of an agent getting a particular item can also be viewed as fractional sharing or time sharing. So it's important for problems where time sharing is involved. Randomization has deep roots in the literature. I mentioned a couple of seminal works here. In particular, the second paper I mentioned, the paper by Bogomolai and Moulin, is actually one of the main inspirations for this piece of work. So let's discuss this algorithm or rule which Bogomolai and Moulin presented in 2001. So the rule's name is called the Probabilistic Serial rule. And let's apply it to this very simple setting where there are three agents, three objects, and each agent expresses their preferences over these objects. So in this case, agent 1 has O1 as the most preferred, then O2, and then O3. So what the rule does is that it simulates an eating process where agents start consuming the most preferred object that has not yet been consumed. So in this case, agent 1 would go for O1, agent 2 and 3 would go for O2. At time half, both agent 2 and 3 have consumed O2, so they will move on to the next most preferred item, which is not yet consumed. So we simulate this process and we continue until all objects have been eaten. In this case, agent 1 ate 3/4 of O1. So this would be an outcome where agent 1's probability of getting O1 would be specified as 3/4. So this matrix at the bottom of the page is basically an outcome of this process, which specifies the probability of an agent getting an item. So when Bogomolai and Moulin presented their rule, they showed that their rule has some distinct advantages over standard rules, especially in terms of fairness as well as efficiency. So one nice contrast they had was that probabilistic serial rule, it satisfies Pareto optimality with respect to first order stochastic dominance, which I summarize as SD. It also satisfies SD NV freeness. On the other hand, random priority or random serial dictatorship violates both of these nice properties. Based on this piece of work, there have been many follow-up works. There are about 600 citations for this paper, and many characterizations of this rule based on fairness, efficiency, and certain other monotonicity properties. The rule has also been extended in various works in computer science and economics. I mentioned just a few, but there are many. So it's been extended to the case of weak preferences, multi-unit demands, individual rationality, upper quotas, and so on. Just to note that our particular rule generalizes all of these rules in the economics and computer science literature at the same time. So in one page, what do we do in this paper? Our main contributions are that we present a general probabilistic rule called the Vigilant eating rule that applies to any closed set of feasibility constraints. Secondly, the outcome of VR satisfies certain desirable efficiency and fairness properties, which I'll briefly mention. And as a case study, we apply this particular rule to the setting where agents have preferences over objects and objects have priorities over agents, which captures the standard school choice or two-sided matching setting. So what is interesting is that when agents preferences are strict and object priorities are strict as well, VR coincides with the deferred acceptance, a well-known deferred acceptance rule. And when the object priorities are flat, which means that objects are completely indifferent among all the agents, then our rules coincides with the probabilistic serial rule. So I've mentioned a few nice things, or I've tried to sell this rule a bit. What exactly is the rule? Well, I will not give you a pseudocode or a formal description of this algorithm, but I will try to give you some intuition behind the rule. So the first basic idea that we use is borrowed directly from a paper by Kata and Sethuraman, which is inspired to handle indifferences in the preferences. So what we do is, instead of working at the level of objects where agents are consuming objects directly, we work at the level of equivalence classes where agents are not specifying which object they want to consume. They're simply specifying that they want to increase the probability weight of the most preferred equivalence class. The second basic idea is also directly follows from the original rule, which is that consumption is irrevocable, which means that once a lower bound has been set on an agent getting certain items, that lower bound can only increase and never decrease. These two ideas one can try to use them directly to handle all kinds of feasibility constraints, but what we noticed was that there were a few challenges that were encountered. So the first challenge we encountered was that when agents are eating objects, a partial allocation that arises from this eating process may not violate any feasibility constraints, but we may have made some decisions which leads to infeasibility in the future. So this challenge is directly met by looking into the future. So we let an agent eat an object only if the resulting partial allocation can be extended to a complete allocation, which is feasible as well. So we need to make these checks whenever we're making some decisions during the algorithm. Secondly, it could be the case that two agents, I and J, can both individually eat an object O, and it does not violate any constraints even in the future. However, both I and J cannot eat object O simultaneously and still maintain this feasibility. So this can, for example, be the case when feasibility constraints are not convex. So our solution for this particular challenge was that we specify an ordering of the agents, and we identify the objects that agents can consume more, given that the previous active agents in that ordering can simultaneously consume more of the designated objects or equivalence classes as well. Note, however, that we don't specify by how much the previous agents need to increase the guarantees, only that they need to increase the guarantees by at least some amount. So once agents have identified, or we have identified the designated equivalence clauses for each agent, so let's say the designated equivalence clause for agent I is EI, then what we do is we simply try to maximize this weight delta, an additional weight which can be put on these active agents while ensuring the previous lower bounds. And this is done while ensuring that in the future, no infeasibility is encountered. So these are some very basic ideas behind the algorithm. What are the properties of this particular rule? So firstly, you take any set of feasibility constraints. As long as this set of feasibility constraints is closed, VR terminates with an outcome which satisfies those feasibility constraints. Secondly, when VR is applied to any closed set of feasibility constraints, it returns an outcome that is constrained SD efficient among the allocations which are feasible. Thirdly, as far as computation is concerned, as long as X is a finite union of polytopes, the outcome of VR can be computed in time, which is polynomial in the number of inequalities used to describe this feasible set. So for example, if we're just dealing with linear inequalities to describe the feasible set, we can solve this problem in polynomial time. The vigilant eating rule also satisfies some nice fairness properties. So the first property that we show is that as long as, for any two agents, as long as the feasible constraints satisfy some technical definition of symmetry and convexity with respect to just that pair of agents, and as long as that pair of agents I and J have the same preferences, then both I and J should get the same outcome. Secondly, if the set of outcomes is convex, then VR satisfies an outcome which satisfies a property called ordinal egalitarianism, which was a property which was proposed by Anna Bogomolai in 2018. I will not go into the technical details of the definition, but it's a very nice and elegant property which is highly egalitarian in nature, and it's especially defined for social choice settings where preferences are ordinal. So as I said earlier, as a case study, we applied the VR rule to the setting where agents have preferences over objects and objects have priorities over agents. So for this particular setting, we already know there's a very nice, well-known rule, the deferred acceptance rule, which does pretty well. It achieves stability and constrained efficiency as long as both agents and objects have strict preferences and priorities. So it gives you stability, but for constrained efficiency, you do need the strict part of the preferences and priorities to maintain this constrained efficiency. So when priorities and preferences are weak, the question arises, how do we achieve fairness, stability, and efficiency? So what we're trying to do here is we're trying to go towards fairness, stability, and efficiency via the route of randomization. So before I go into some properties of VR in this context, I just want to mention that in the world of probabilistic matchings, where both sides have preferences or priorities over each other, there are many different notions of stability which generalize the standard stability concept in the matching literature. So I highlight here 4 standard concepts which are meaningful in the case of probabilistic matchings. They are ex-ante stability, ex-post stability, fraction stability, and claim-wise stability. As you can judge from at least the name of ex-post stability, it simply means that the outcome can be represented as a convex combination of ex-post stable outcomes. I will not go over the other definitions, but what is nice is that as long as the matchings are deterministic, all of these 4 concepts, they coincide with the standard stability concept in the case of deterministic matchings. So what we did was we treated all of these stability concepts as feasibility constraints. So we just treat it as a generic stability concept S. It leads to corresponding stability constraints, feasibility constraints. And what we did was that we term SVER as the VER rule, which is applied to this two-sided matching problem where the feasible constraints are according to the stability concept S. So when we do that, we identify which properties are satisfied or violated by this particular VER rule. So just because we know that VER satisfies feasibility constraints, so we directly get that VER satisfies S stability. We also get from our general results that SVER satisfies SD efficiency constrained to the set of S stable outcomes. Again, from the general results, we get the result that SVER satisfies equal treatment of equals. Another nice insight we had was that SVER coincides with the agent proposing deferred acceptance rule when both agents' preferences are strict as well as. On the other hand, SVER does not satisfy SD efficiency in the global sense. It's not weak SD strategy proof, and it's also not satisfying this property called weak SD NV-freeness, which the original probabilistic serial mechanism does satisfy. However, these negative results are not a drawback of SVER, because we show that as long as any rule satisfies these three properties satisfied by SVER, or any mechanism satisfies these properties, then it cannot satisfy these additional properties which are violated. And this is done in a form of three impossibility results. So I will quickly mention that there may not be any allocation that is claim-wise stable and SD efficient. The set of weak SDNV free and set of claim-wise stable allocations can be disjoint. Recall that claim-wise is actually the weakest concept in this hierarchy of concepts that we were considering. And finally, there exists no mechanism that satisfies weak SD strategy proofness, S stability, and S constraint efficiency. So in the form of these three impossibility results, we can say that at least the properties satisfied in this table are a maximal set of properties satisfied by SVER. So I tried to frame this particular rule, the vigilant eating rule, in the form of object allocation, where agents have preferences over objects. However, in our paper, we discussed that the VER rule is not restricted to the case of object allocation. It can apply to any social choice context where agents express ordinal preferences over a finite set of deterministic outcomes. So in this context, it applies directly to probabilistic voting. It applies to participatory budgeting, especially when there are complex constraints involved in participatory budgeting, such as enforcing some lower bound on amount of money allocated to a certain project. It also applies to more complex preferences, as well as two-sided random matching, which is in the true sense two-sided matching, where both sides are agents and they're both eating at the same time. So we also discussed in our paper how we are, with respect to particular constraints, capture many known rules in the literature. So I'll quickly go over a few of them. It's an extensive table. So obviously, when there are no constraints, and the preferences are strict, then we are directly coincides with the well-known probabilistic serial rule. This was our starting point. If, let's say, we impose the constraint of SD individual rationality and the preferences are strict, then the rule coincides with the control consuming rule of Atansoglu and Seturaman. VER also generalizes many other rules which have been presented in the last few years, including the generalized probabilistics rule by Budish et al. In their AER paper. Another generalized probabilistic serial rule which was proposed last year by Ashlagi et al. In the SODA paper. And also it generalizes the egalitarian simultaneous reservation rule, which I worked on with Paul Struisberg in 2014, which is in the context of probabilistic voting. A couple of things I want to mention here. I already mentioned that if, let's say, the constraints are ex post stability and preferences are strict and priorities are strict, the rule coincides with the agent proposing deferred acceptance algorithm of Gale and Shapley. I'll just mention of one other coincidence, which is that if, let's say, the constraints are such that we are only allowed to have integral allocations, and agents have single unit demands and preferences are strict, then we are also coincides with this well-known serial dictatorship rule, which is in the last row of this table. So it unifies many known rules in the computer science and economics literature. So to conclude, we presented a robust preference aggregation rule that applies to any closed set of feasibility constraints. Considering that many matching applications are essentially people have to reconfigure or tweak the well-known algorithms to cater for new feasibility constraints or new application domains, what we've done is we've identified a very robust aggregation rule that can apply to any feasibility constraints and therefore for many applications as well. We showed that it has desirable fairness and efficiency properties. And to showcase that, we focused on this case study where agents have preferences over objects and objects have priorities over agents. And in that sense, we showed that it leads to certain new rules which can be applied with respect to well-known stability concepts. Note here that previously, at least in probabilistic allocations where both sides have preferences, there hasn't been much work on probabilistic matching algorithms with two-sided preferences. And this concludes my presentation. Thank you.
Thanks, Harry. So let's unmute our microphones and a round of applause for Harry. Thanks, everyone. So at the moment, I can see one question in the chat by Christian Stricker. So Harry, do you want to pick that up?
Which question was it?
So Christian is asking if your rule can be applied to stable roommate matching.
It applies to as I said earlier, it applies to any kind of social choice setting where agents have preferences over, ordinal preferences over social outcomes. So indeed, it applies to stable matching as well, a stable roommate matching as well.
There's a question for Felix. Harris, do you want me to read it out loud or?
No, I can see it. Felix, who has been working on probabilistic voting for many years, his insight is absolutely correct. That if in the context of voting, our rule simply coincides with the ESR rule, so thereby it will return a uniform lottery over all first-rank alternatives, which are in the support of the agent's preferences. Yes. Christian asks, okay, I've already answered that.
So I have a question. So do you have examples when this rule can be used, but isn't polynomial time implementable? So a natural setting where it's usable, but seems to lead to something NP hard.
So I mentioned I mentioned 4 stability concepts. 2 of those concepts can be claim-wise stability. Let me just unshare my slides because Ole instructed me. Actually, I have unshared. Yeah,
I've unshared them for you already.
Okay, great. Okay, thanks. So out of the 4 stability concepts, 2 of them, claim-wise stability and fraction stability, can be captured by just writing down linear constraints. Ex post stability can be written down as linear constraints as well, as long as preferences and priorities are strict. When you have indifferences, it's actually not clear whether ex post stability can be written as a convex combination of linear inequalities, and in particular, ex ante stability is a non-convex concept. So it's not even clear what the running time of applying VR to ex ante stability is. But it's a well-defined rule for ex ante stability as well, and it satisfies nice properties because people are really like ex ante stability, which is a very strong stability concept. So if you're curious about which nice, meaningful constraints lead to intriguing computational questions, that's probably something which we haven't figured out yet.
Thanks. And there's another question. There are 2 more questions in the chat.
What if only partial ordinal preferences are given? Does this idea still remain generalizable? Yes, as long as there are no cycles in the preference relation. Kata and Sethu Raman gave this idea that you can easily do topological sorting over this partial order, and you can still get the same result. So it's well defined for partial orders as well. And instead of agents consuming the most preferred objects, they simply go for all undominated objects at that point. A very minor point, why give this particular name to a rule with this high potential to generalize various mechanisms? I think it's a very natural, it's an eating, I find eating algorithm as a more capturing probabilistic serial rule a bit better. And one of the key features of our algorithm is it's highly vigilant in its nature because it's always keeping checks on before making some decisions. So for those reasons, we chose this name, but we are still open to naming the rule. Yeah.
Further questions, anyone? Any format? Okay, so if not, then let's wrap up for today. Let's thank the speakers again.
Thank you.
And so Ulla, do you want to say a couple of words about our next session?
Yes, so we're still going to have a break next week, and then we'll start again with more or less weekly seminars, usually on Thursdays, but in 2 weeks' time it will be a Friday, because on the Thursday there will be 3 computational social choice sessions at ECAI, which is an online conference that you can all participate in. And on that Friday, in 2 weeks' time, we're going to have Dorothea Baumeister and Siddharth Barman talking about voting and fair division. And I'm sure it's going to be great, and I hope to see you all there.
Thanks again, everyone. That will be the end of the seminar for today.
Thanks for hosting, Ole and Edith.